Okay, now I'm gonna do a fresh start here and just to make sure that there's nothing maybe wrong with the other one or unclear. Maybe I can do a better job if I do it again. So anyways, I'm starting out with the constant voltage, and we have current, and our goal is to plot 1 over R as a function of the current. So that means the current is on the x-axis and 1 over R is on the y-axis. So this data was taken with and recorded in centimeters. I think a half a centimeter is kind of a lot. I'm sure most of us did like 0.2 centimeters or 0.3. I mean, 0.5 is not unusual. It's not outrageous. Okay, so we have to convert it to radius, of course, so we divide by 2. And we have to also convert to meters, so we divide that by 2. And we type that in, and we use the fill handle. So, and then it's the same thing with the plus minus. Basically, what you're preserving is if you have a measurement with a plus minus, remember that there's the so-called fractional error. So if it's the fractional error on the diameter, oh, hold on, I got a thing to fix the tablet driver. So I'm back. So the so-called fractional error is equal to the plus minus d diameter over the diameter. So if I divide the diameter by 2 and I divide the plus minus by 2, you see that I get the same thing. I preserve the fractional error, the ratio. And of course, I'm also going to divide by 100 in both cases so that I convert from meters to centimeters, or centimeters to meters, excuse me. Okay. All right, so of course, 1 over R is pretty easy to do, right? Equals 1, equals 1 divided by R here. And then we can drag that, fill it up. And what do we do about the plus minus? Okay, so we have our formulas. So here they go. And and let's get this out of the way. We need that a little later. And we can make this smaller. I think we can make it smaller still. There we go. So we look at this obviously 2 quantities multiplied, 2 quantities divided. So in our case, we have the 1 over R. So the equals, well, 1 over r. I mean, it's kind of hard to write that out without sounding foolish. But if we go to the plus minus 1 over r, so in this case, a is 1, b is r, and the 1 is a constant. It doesn't have a plus minus. So we have to put the quantity and times plus minus a over a squared. Well, it's plus minus 1 over 1 squared. But plus minus 1 is 0. There's no plus minus, so that's a 0. Let's make that neater. Okay. Putting real numbers in here now. Well, yeah, so it's the plus minus of the 1 divided by 1 squared, so we'll still say symbols, plus minus r over r squared to 1/2. And this is 0 because the plus minus is 0. And so this is just this term squared and square rooted. So the plus minus, this is how we do it, put it into parentheses, equals the value of 1 over r, and just simply plus minus r over r. And that makes sense because this is the fractional error. So if we know the fractional error on r, we have to maintain that fractional error. So we just take the value and multiply it by that fraction, and that tells us what part of 1 over r is the plus minus. So it's pretty straightforward. So equals, and the temptation here sometimes is to like multiply these r's together or cancel them, and that's why I put the parentheses in a way to try to say no, you can't do that. Okay, so equals the 1 over r times the plus minus r divided by r. We don't need parentheses, and that's our plus minus down the line. Okay, so now we'll get rid of this if we can. There we go. Oops. Okay, so now we need a fit line. And let's see what we got. Well, first, let's see. First, we want to plot this. That's right, because if we put the fit line on there and then we put the error bars on, we're going to have to deal with 2 sets of error bars. So if I put the error bars on now, then I won't have to worry. I just have to deal with the plot of the data. So I select the amps, the I, the different currents, and I hold down the control key and 1 over R, insert, and I want a scatter plot, and there she is. Pretty looking, huh? And then I need, let's see, I thought that this was highlighted, so, oh, there it is, chart design. And we want to add error bars, and we'll call it the standard error. And then we want to bring up that format box over there, yep. And I need to make room to access that. And I suppose we have to act like we have a Macintosh, because this is true for Macs and PCs, so do it this way. Bar chart here, and the x error bars are 0, because that's the independent variable. Okay, and then we want to format and the y error bars, and that's going to be custom, and we specify value, and it's symmetric, we just use them for the plus and the minus. And there's our error bars. Now, one thing I see that those dots are pretty big, so I'm going to make them a little smaller. There we go. Oh yeah, when you do automatic, you can't do anything about it. So we hit built-in, and now it's nice and small. Sometimes I might even make them hollow if maybe I want to see if there were other data points of a different color. This way I'd be able to see them if they fell behind there. Okay, to fill, we'll put that back. Oops. What happened? I'm no longer editing the data set, apparently. Oh, not no fill. Let's see if we can hit the undo button. There we go. Okay, so what happened to formatting the data series? There it is. Marker, and solid fill is back. Okay, nice. Alright, now let's make the fit line. And we want to just estimate our, so something times 1 is equal to 18. That looks hard, right? So we can make a first guess at a slope as 18. And let's make a guess at the y-intercept. Looks like 6 or 7. All right. Cool. All right. So now we say equals to the slope. And now we need the $sign, so you can just click in here and manually type in the $sign. Oops, not percent, dollar, then dollar. And then now I need to, because I got this zoomed in, I can't see. Here it is, the current, and then plus. I'm doing the scroll bar on the bottom. Oh, I forgot. Maybe that helps me. And then I click on the y-intercept. And I remember to put my $signs. Coolio. And then I fill. Now another thing I'm going to do is I'm going to add a 0 point here because I want the fit line to go all the way down to the x-axis, all the way across on the left side to the y-axis. And then I want it to go past the last data point, which looks like a 2 will get the job done because the largest x value at the moment is 1.8. And Excel seems to know that I want to do that, and it just filled those in for me. Okay, so we can, next step then is to add the fit line. And now we do select data. And we add. And the name is fit line. The X values are these amp settings. And the Y values are the formula here, these guys. And then, oops, okay. And we see right off the bat that slope looks pretty good. Let's try just using 0. And that makes it look a lot better. So now we just need to turn that into a line. Format. And we want data series, fit line. And oh, we're not getting the bar on the right, so I'm just going to go click, click. And there we go. And then now I got to do this again. Format. And data series, fit line. Solid line. And let's try this tomato. Dark red today instead of plain old red. Live dangerously. And to make it small. And I want to get rid of the markers. None. Okay. Now we are on our way. That looks pretty good. And we want to now do our residuals and residual squares so we can get the best possible fit. So this is equal to the data minus the fit, and that's it. And we fill it in. Remember, only to do it for actual data. Well, I don't know what it'll do here. Complain? No. But those are, well, a 0 is not surprising, but a negative 36 should tip you off that something's wrong. Okay, now we simply square it. Equals this squared and now we need to get into this chi-squared, and I'll go back over that. Okay, so the chi-squared is what you see up here, and one thing I left that's not on here should have been, let's see if we can reproduce that color. We'll try. I don't think so though. This is more purplish. That's not the right one. But anyways, this one should have an I too, because it's just the res squared divided by the plus. Sigma is just another way of saying plus minus. And what this does is that, first of all, if you, well, you guys apparently have never done this with a plain piece of paper and a ruler. But remember, the general rule is that the sum of the distances above should equal the sum of the distances below. But at the same time, it should pass through all the different error bars. And if we, and you might have encountered this, if I have a data point way out here, and we say, boy, there must have been a mistake there. And in fact, hopefully, this data point comes with a big error bar. And so we can still have the line pass through all the error bars. And we know that this point is not quite so important as the other points. Now, for a human being with their Mark 1 eyeball, you can downplay that point. But as always, we want to teach the computer how to do it. And remember that our figure of merit for a good fit is the minimum value of the res squared. So the chi-square is you can imagine that now we can do the sum of the chi-square, and you say, okay, great, but how does it minimize the impact? Well, let's take a look here. Let's create it first. Equals the res squared divided by, excuse me, oh, I gotta get this out of the way. Oops. Oh, come on. All right. Yes, I'll accept your correction. All right. So now it equals the res squared divided by the error bar on that point, and so and then we need the caret n squared. Okay, so let's take a look here. So you notice these numbers are all kind of the same, and let's see about let's put a big plus minus on here. 5, right? Now, notice that this number became smaller. So when I sum this thing, this number has less impact. In fact, we can look at it a different way. Put that back to what it was. So this one is equal to the sum of the res squared and this one is equal to the sum, wow, I gotta get rolling, look at the time, of the chi-square. So I'm gonna have to stop this soon and pick it up later. I got an optometrist appointment with Jenny. Okay, now if we increase the error, then let's make it 8 and watch the chi-square. When I hit this, you see it got smaller. So that means that that particular point has less influence on the sum of the chi-square. And remember, this is what we're going to use for our minimization. So in fact, we can do our first we can do at least do that much before I have to leave. So it's the sum of the chi-square, and we wanted to change the slope and the y-intercept, and we make sure non-negative is unchecked, and we hit solve, and ideally we look at the graph, because remember, this can't be undone for some reason, but we see that it looks nice, and we see that that it's smaller. In fact, what we can do is, let's try the same thing, but let's use the, instead of the sum of the chi-square, let's use the sum of the res squared. And this is not the most smallest value for that, we're going to notice. I mean, notice it says 3.99, and we say okay, and now it says 3.86. It's even smaller, but the chi-square got bigger. And what you see is that this point here kind of pulled it down a little bit, and because it got equally weighted. So we'll go back to the sum of the chi-square. And now, sum of the chi-square here. And then we hit solve. Oh, the slope got less, so that's interesting. So without the chi-square, it got pulled up. I don't get. But of course, maybe I should have held this constant. But in any event, at least you see that they're not, if I minimize one or the other, I don't get the same answer. I guess I'll have to make an example with a data point that's really out there and then do what I just did. But in any event, I gotta fly because I don't want to be late. Jenny's waiting for me there. Well, maybe I'll be waiting for her, but then I win in the battle of marriage. Or at least I win this battle until the next one. The ongoing war of marriage. Okay. See you soon.